In this video, I'm just going to show you how to set up the virtual wind tunnel case in Swift. Virtual wind tunnel allows you to calculate multiple wind angles in a single calculation, and it forms a basis for a lot of the capabilities of Swift in terms of external CFD, facade pressures, and so on and so on. This tutorial here is available for download from the Swift homepage. If you scroll down to download files, you'll find it here, virtual wind tunnel, multiple wind directions. The canvas in Grasshopper looks a bit scary, but that's because all of the green boxes here are just commentary from myself explaining what all these do. So actually the layout is quite streamlined and quite simple once you get used to it. Just so you know what the results look like, here is the results loaded up into Paraview, and you can see we've got a very simple domain, external CFD, fine, but you can see then we get multiple wind angles solved. And you can see the results are only valid for within the turntable. That's because of the way that we rotate the mesh and map the results back onto a single mesh. But doing this allows us to carry out some more sophisticated analyses, which is just not possible using multiple meshes and then mapping, or it could be very challenging. Doing it this way is very swift, it's very fast, and it allows you to do some very neat post-processing, which we'll come to in later tutorials. So let's go back and get started and see how to create this. So what I did just to save time was I copied the BREPs across from the actual virtual wind tunnel tutorial, but you could draw these rectangles yourself in Rhino. You don't have to internalize them to Grasshopper if you don't want, it's up to you. Next thing to do is to add a CFD domain, and this just places a basic domain around the boxes, and I think in the tutorial we use a cell size of 2. You can adjust all this later. And you can see when you do that, it places the domain around the box, just a simple square domain. By default, Z0, center X, Y, and square are set to true, but I just like to hook these up just to make sure. That tells the CFD domain to be centered around the XY, to be square in shape, and to be based at Z equals 0. The next thing to do is to actually mesh your BREPs, because most analysis software like OpenFOAM, Energy Plus, and Radiance all rely upon triangulated primitive meshes. So this block mesh BREP allows you to create your primitive mesh, and you can adjust the parameters here if you want a more refined mesh. But for now this will be fine. We also want to just get the names from the BREP objects. Now by default it just gets the basic GUIDs, but you can actually set names back here if you wanted to assign a specific name to certain BREPs, but we'll get onto that in a later tutorial. You then want to actually set the names for those primitive mesh objects. Here's your objects, and there's the names that have been retrieved from the BREPs. It's also a good idea to actually set the names for the original BREPs again. That just ensures that all the names have been captured and set according to the list of BREPs. So that's the reason why this block looks like this. Next thing to do is you want to set a CFD mesh level, and in this case we'll just take all of our BREP objects that have been named. You want named BREPs coming in there, and we'll set a mesh level in this case of say 2. You can add more mesh levels obviously if you'd like, and you can select these BREPs in a more strategic way, and the outer ones might be at a lower level than the inner ones, but for this basic tutorial, we'll just set them all to the same level. So now we've got all of the information in here for a very basic mesh. So we want to add in a CFD mesh object, and we add in our domain. All of the primitive surfaces, so the actual triangulated mesh objects, and set all the mesh levels. You can obviously assign refinement regions, boundary meshes, and other more advanced features, but for now we'll just go with a basic mesh. We'll hook a button up to write files, and the only other thing that we need is to define the CFD keep point. So we'll use the default that's provided by the CFD domain, and we put that into the overrides. Now you can interrupt this pipe and redefine it and feed in a different CFD keep point if you'd like, but for now, in this demo, that'll work just fine. So the final thing to do is just to define where this case directory will be written. So to do that, we just define a panel, and we set the variable case dir, and we set that to C drive ODS virtual wind tunnel foam, let's say. And that is where the base case directory for this will be stored. Make sure that you always finish a definition with a semicolon if it's going to go into the overrides, otherwise it won't be written. And so we add that into the overrides. You can, if you like, add in a case directory component, which allows you to control the deletion of the case directory and the processor files inside of it. It's not necessary, but it's nice to have if you're doing a lot of iterations and wanting to clear the directory very often. So now we have everything set up to write a basic mesh, and if we click Write Files here and click the button, you'll see that it creates a virtual wind tunnel folder. Now it hasn't got any boundary conditions set, and it's only got the basics required for basic mesh. So at this point it's actually good to set up a run solver, and you want to run that mesh and inspect what the mesh looks like before you go too much further. So in this case we'll set up a panel and we'll define the solvers that we want it to be is block mesh and snappy hex mesh. I've got a 4-core computer, so I'll define the domain to be divided 2 times in the X, 2 in the Y, and 1 in the Z to give me 4 subdomains that will be divided up for multiprocessing. And in this case, we'll just run it using a button. By default, the cases are reconstructed after the solvers have been run, so we don't need to modify that. At this point, we can run the mesh function, and you can see it's going through the process of running block mesh, running snappy hex mesh, and then reconstructing the case. If you look on the CPU usage, you can see that all 4 CPUs are being utilized. At this point, we can open up ParaView, go to C drive, ODS, virtual wind tunnel, and inspect the mesh. Load all the cases in, look at it in wireframe, and you can see the mesh there. The one thing you want to be sure of is that none of the cells on the outer surface have been subdivided. You need the entire mesh to remain subdivided inside. Otherwise you won't get a clean join between this mesh and the rotating turntable. So that's the meshing process, and it looks like we got an okay mesh, so let's continue on. So now that we've got an okay looking mesh, we'll set up the rest of the case, including the boundary conditions and the solver. So we'll add a CFD solver component, and this will actually add in all of the remaining files, such as boundary conditions and everything that's required to actually run an actual solution. We define a solver. In this case we'll use SimpleFoam. The patches are the same as what came out of the mesh. Now we need to add some boundary conditions. So to add boundary conditions, we just add a CFD BC component, and by default all the objects are wall type objects, and the CFD domain has special names on the outer patches of minx, maxx, minY, maxy, minz, maxz, and so on. We'll keep all the default wall conditions as they are. However, we want to define an inlet flow velocity of 5 meters per second on the maxy. So we'll override those, and we'll set an outlet boundary condition of fixed pressure on the min-y side. So to do that, we add a panel and set maxy. We'll use a preset condition in this case. I'll explain what these presets are in a little bit, but for now, let's just use a preset of fixed velocity. Fixed velocity by default just defines a null velocity or 0, so we actually need to override the fixed velocity definition with u is equal to value uniform 0 minus 5 0. Don't forget to end with a semicolon. This is just a standard dictionary override definition, which we'll talk about later. We want to add another boundary condition for the outlet condition on the min-y. So this is min-y. In this case, we just want to use fixed pressure. The default definition for fixed pressure is a fixed pressure of 0, which is fine in this case. We don't need to override it with any special values. For the remainder of the surfaces in the virtual wind tunnel, because this is quite a small demonstration, we'll set slip velocities to all the remaining surfaces, including the ground plane, just because we're using a coarse mesh and we won't be able to resolve the boundary layer very well. So in this case, we'll get a little bit more realistic results if we set the ground plane to have a slip velocity also. So in this case, we want to set min-x max x, min z, and max z to a type of wall slip. Now it's very important that the inlets for these are multi-line data, as they're read in as a list. Obviously, if you had particular surfaces, buildings, or more complicated geometry, you just grab the names using the getNames component from your original BREPs, and you can feed them into the boundary condition object. So you don't need to manually type every boundary condition name like this. So you can quite quickly construct quite complicated models just using getNames, setNames, and boundary conditions. We'll feed these boundary condition objects into the solver. Now you might be wondering where these presets come from and how I know they should be overridden. You can inspect the presets by connecting a panel up to the preset outlet of the solver. And here you'll have, for a given type, wall, wall slip, and fixed velocity, and so on. I've provided a few default common preset boundary conditions. However, you can easily append and add to this file by just copying this text file, adding to it, and you can overwrite in the preset overrides. In this case, you can see for max y, we've used the fixed velocity, and you can see all the boundary conditions that are going to be applied for the fixed velocity type preset. However, we only want to override the value uniform 0, 0, 0 in order to provide our -5 meters per second on the inlet patch. So that's the way the presets work. It allows you to build up quite a large library, which you can easily transport from one Grasshopper model to the other. And it allows you to create very complex models with a very small number of definitions and overrides. Now that we've defined the solver, we want these solver files to be written at the same time as we write the mesh files. So we connect the files written from the CFD mesh into the write files of the CFD solver. After the solver files are written, we want to then run the meshing commands. So we connect files written into the run. Obviously, you don't have to do this. You can manually control the meshing and the running of the various solvers by pressing buttons. However, if you want to run a parametric study, you'll need to connect these up into a long chain of commands. We've already defined and tested the meshing, so we know that that works. So after the meshing has been done, we want to queue up a virtual wind tunnel for running. So after these have been queued, we run the virtual wind tunnel. The number of CPUs is the same, still 4. The solver that we're using is output here, or you can use this one. It's just a definition of the solver that will be used to run all the different wind angles. The mesh are the dimensions of the mesh, which for now is output from the CFD domain. It's just basic mesh dimensions which are used to calculate the virtual wind tunnel requirements. The angular step we'll set now, say 14. And you can see the effect that this has by hooking a panel up to the number of angles. You can see in this case that we're going to calculate 8 angles at a step size of 45 degrees. If we increase the angular step, we'll calculate fewer angles with a larger angular size. So this will calculate 3 angles at 120 degree increments. Similarly, if we make it smaller, we'll calculate more angles at a smaller step size. The angular step is the number of cells across our CFD domain that we're going to rotate the mesh every time. So if we have 90 by 90 domain, and we have an angular step of 1, we're going to step at 1 degree increments. In theory, you could run a full 360 degrees at 1 degree increments. The number of iterations we use for the very first step will be 50, and we'll also use for this demo case the same number of iterations for future subsequent iterations. The reason you define these twice is because if you have a large number of angles, say you are doing a full 360, you'll want to run the first angle for a large number of iterations, and then subsequent iterations use the results from the previous angle as a starting point for the current angle. So if you have a very small angular step size, you won't need to run a very high number of iterations for all the subsequent angles, because they're only incremental changes from the previous angle. So that's it, the case is all set up now. We're going to write the mesh files, write the solver files and boundary conditions to create a full case, which will work for SimpleFoam. we're going to run the meshing commands, block mesh and snappy hex mesh, across 4 CPUs, and then we're going to solve for 8 wind directions at an angular step size of 45 degrees. These will all be run sequentially as we press a button. So let's delete our previous folder and see how it runs. Press a button. You can see the case file's been written again. This time all the boundary conditions are defined. You can see at the moment that it's going through the meshing command of snappy hex mesh with 4 CPUs. After it's finished meshing, it backs up the original case. You can see what angle is being calculated at any given time by looking at the number that's in your virtual wind tunnel directory. If there are 2 numbers, then one of them will be the current one calculating, and the next one will be the one that's being set up. As one case is running, the next one's being set up in the background so that you're making maximum use of your CPUs and it's running as fast as possible. You'll know when it's finished calculating because you won't see any more bash windows pop up down in the bottom taskbar, and when you inspect your virtual wind tunnel directory, you'll see there's no more angles being calculated, and all of the angles that you've assigned at 45 degree increments are finished here in the VWT directory. At this point you can start up ParaView to view the results, navigate to the virtual wind tunnel directory, and open up the case.foam file. It's important when you're viewing the results, if you're looking at the velocity, to look at utrans. This is the transformed velocity, which is mapped back onto the original 0 mesh. You can take a slice in the Z direction, at say 2 meters. You can change the preset color scheme to ERDC rainbow, or whatever you like, and you can add glyphs. If you're going to add glyphs, make sure that you're always looking at the utrans. You must always look at the transformed velocity vectors. If you don't use utrans and you use the original U, you'll see that the vectors will be incorrect for later wind angles, but utrans corrects those vectors. You can also obviously add streamlines, and so long as the vectors are based on utrans, they'll be correct for all. So that's it. That's how you use Swift and the virtual wind tunnel to solve for multiple wind angles using CFD and Grasshopper. Please support this project. You can contact us directly or go to Patreon to look at our individual or corporate supporter packages with associated rewards.